All right, so welcome everybody. My name is Andreas Fertig. I work as a trainer and consultant, obviously for C++. And welcome to this very special day. I'm not sure whether you're aware how special it is today. You might not be able to know, but you are part of the group enjoying, hopefully, I mean, they closed the blinds, so not the wonderful view here, but the talk at the highest floor I ever gave so far, 43. I thought it was 44, but I had to go one floor down, right? But I've never been at the 44th floor, and I checked why that would be, and it turns out that at least according to Wikipedia, in Germany there are roughly only 3 buildings that have that many floors. So it's difficult to getting higher, and you're also outscoring New York meetup next week, or no, Thursday this week. They managed to put me up at the 38th floor, I think. So this is still the highest one, and I think it will remain that for a while. So topic of today is C++ Insights. This is the tool I created, and it helps you peeking behind the curtains of your compiler. And what that means, well, I will explain that to you during this talk. I'm German. My last name is not a very typical German name, but a very typical German word. You can translate it into English as finished, ready, complete, completed. So it's a very nice name, right? So you're always ready, not to confuse with too wasted after a day. But it's really great. And in German, my last name, of course, as in other languages, starts with a capital first letter. It's an adjective if you use it in a sentence, so that's a lower first letter. So the spell checker and I have a constant fight, and we are still discussing who is right, when, and where. But while preparing this talk, I realized something different than usual. You might be aware that the Olympic Games start by the end of the week, right, in France, and a lot of people speak French here, I assume. I can only say that I don't speak French in French. And you know that if you start a race, swimming or running, it's, in English, it's ready, steady, go. It's really simple, really nice, and then you start running faster than Usain Bolt, and I just read that we all might have a chance because he has a little bit of problem with his feet, so maybe we could outrun him. Anyways, so it's ready, steady, go. It's real simple commands, and the first command translates to my name, my last name. So whenever they start Olympic Games, they use my last name. Now here's the thing, because I also speak German, I translated that to German. Here's the German translation. It's auf die Plätze, fertig, los. The interesting thing is, we need 3 words for the first command, so you have to listen very careful, otherwise you start running too soon, right? If you're trained to run at a third word, would be too soon. So you have to watch out that, and if you just learned how my name translates and you use it as the first command, it's wrong, because in German we put it as the second for whatever reason. So looks like languages are hard, right? The spoken ones and the ones we only type. So let's go over to the ones that we only type. C++ Insights, this is, as I said, the tool I developed. So this is the tool I have. Oh, all right, okay. No, that's the other tool. That's Compiler Explorer, right? Who here knows Compiler Explorer, just by a show of hands? Oh, that's nice. Okay, everybody knows Compiler Explorer these days. So that's really great. You know it, right? You put C++ code in, you get assembler code out, or you can execute that thing. I use C++ Insights a lot during, or sorry, Compiler Explorer a lot during my training classes, so it's a perfect tool for teaching. But at the end, I'm a C++ developer, and there was a time when I was better in assembly language, but it fades a little. I'm concentrating on C++ code now. So I wanted to talk about this tool up right here, because Compiler Explorer links conveniently to C++ and C and C++ Insights links back. So this here now is the tool I want to talk about. And it's highly inspired by Matt Godbold's Compiler Explorer. You punch in your C++ code on the left, and you get C++ code out on the right. I still think it's $1 million idea, but haven't found somebody who agrees to give me that amount of money. Okay, as you can see, the interesting difference, of course, it's not just the C++ code you wrote. It's enriched by the knowledge of the compiler, what the compiler has to do to make your code actually compile. And what you see here is the transformation of a range-based for loop. So this is what's behind a range-based for loop. All right. So C++ Insights, the purpose is to show what's going on under the hood. Make the invisible things visible again. I like C++ a lot, but it's a very implicit language. And I like that I can write compressed code there, but sometimes we want to visualize what's going on, to see what's going on, either for teaching or for hunting bugs to understand better how our code behaves. And my day job is teaching, so I created C++ Insights mainly for teaching, because what I learned from Compiler Explorer is that if we can make the things seen, if we can more or less touch them, if we can change the code and see the result, this is where things really get started, and not me having to explain in thin air a 5-line program and nobody could follow me, and then somebody asks the question, what happens if I change that? And it's a mess. But having the ability to write it and to execute it, to see it, I think this is where things really excel. So it's for assisting you with teaching or when hunting bugs, when explaining things. The goal here is to create valid code out of C++ Insights. So the transformed code, the result, should be valid C++ code again. This is mainly for the reason that I'm able to test what I'm producing here, the result of the transformation. In my book, since we are all programmers, I think the language wouldn't really matter, but code is the most important thing, right? If you're giving a talk, if you're reading books, if I show wrong code at any point and you later try it out at home and you think, okay, what did he say and why isn't it working? That's just frustrating. So the reason here is creating valid code to be able to play with it, to see how things really go. That also means that the code that C++ Insights produces should be able to compile again if you punch it into, let's say, GCC or Clang again. Of course, the tool itself is open source. It's using Clang's infrastructure and making it open source is just, I think, a natural thing. Now, if you like the tool at the end of the presentation, but you still don't trust me, which would be all right, you can run a local instance of C++ Insights, like for Compiler Explorer, to, well, do not expose your company confidential algorithms and source code to a machine you don't know, where you only seen the guy develop the tool, and, well, maybe not that trustworthy, right? So you can run it locally. There is a link that explains it. It runs in a Docker container, so if you already have a Compiler Explorer instance running, it should be easy to add C++ Insights to that. C++ Insights is a Clang-based tool. That means it's comparable to something like Clang Tidy. It uses the abstract syntax tree, the AST, from Clang and transforms that one back to C++ code again. So it's way more than a preprocessor. In a typical compiler pipeline, we have a front end, a middle end, and back end. And C++ Insights works with the front end of Clang. I believe Clang doesn't have the notation for a middle end. They only have a front and a back end. And the front end is responsible for parsing, creating your abstract syntax tree, validating all your source code, and then handing that off to the back end. The back end, in the end, generates your binary source code or your binary code. And the back end also does the optimizations. So this is one reason why C++ Insights does not expose things like -03. It wouldn't make any difference for the output of C++ Insights because the optimizations run later. I have no glimpse into that. So just to be aware, it changes your program, of course, but not at this stage. C++ Insights, the website at least, tries to use the latest official version of Clang, latest release version here. That means that maybe not all the latest features from C++26 are already available at the website. Maybe you have to wait for one cycle, despite that they may be already in Clang trunk. One thing that sometimes is nice and sometimes it's too much is thanks to the abilities of Clang itself to work with two different standard libraries, libstd.c++ from GCC and libc++, both libraries are supported in C++ Insights as well. So you can flip which standard library you want to use. Sometimes it helps because the one already supports a feature, the other doesn't. And the output, if you look behind the scenes, changes slightly, so the implementations for the standard library. This is usually nothing I'm too keen to show, but it simply pops up because it's part of your C++ source code. Potentially not all C++ statements are currently matched since the language evolves, so there might be C++ 23, 26 statements out there that are not supported. Some could be the reason that Clang doesn't support them at the moment. Some I might have not catched up with what I implemented recently. I said I want to create valid code out of C++ Insights. And this is a tough challenge, so I gave up at certain points. Templates are a very tough thing to create valid code out of. Here's one example. I have this very simple, silly function template func. It takes a single template parameter t, and I have this class demo in there, and in main I'm instantiating and calling func with the type demo and call the function essentially. If so, that would happen. If I use C++ Insights now to transform that, so this here would be C++ Insights, and if I hit transform here and do the transformation, then we can see it tells me the primary template at the top here. Then we have the instantiation, which also conveniently shows the first line number from the left-hand side where it was instantiated or requested from. And there we can see that I put this instantiation behind this ifdef insights use template. And the reason is, here's the class demo, and here is the call to func. And whether the resulting code here now compiles or not depends on where you put your class demo. I have to make a decision when or where to put the instantiation of the function template func. The same would be true for a class template. And I usually put it directly after the primary template. Well, that means that in this case here, the code that I'm generating is not valid, because I use the name demo or the type demo before it's really declared. So I would have to make it really work, to really compile, to put this instantiation behind the class demo behind the first occurrence. And it would be possible to do it here, but there are more complex scenarios where I simply gave up and said, okay, I put this behind the ifdef, you still see what the result is, and if you move it around, you can make it to work, but in a lot of instances, it's way harder than that. For example, if the type comes from a third-party library or things like that. By the way, if you have any questions, feel free to ask. So what is an AST, an abstract syntax tree? This here is an AST. And when I created C++ Insights, one goal was to not have to read the AST, because that's the real truth. So nobody needs C++ Insights. You simply can use Clang and dump the AST. You see everything that's going on there. the same view as C++ insights, just not in C++ source code, but it's what your compiler spits out. So, any idea what you're looking at here? Aside from that's an AST, of course, the program behind it. Please.
Hello, C++ going out to C out.
Something going to C out? Yeah. Anybody else? Anybody happy with C out? As I said, when I started, yes, please.
I think that's it says int. It says int.
Yeah, it says int. Yeah, it has an int in there. True. So let me help you out there. You all know that. It's a hello world. Okay, it's the thing we start in every language with. It's just a hello world. So it has the int in there. It's the return type of main. It has the cout. So yeah, as I said, when I started, I didn't want to be able to read that. It turns out nowadays I feel more like Neo. I can read the matrix now and decipher it because I'm quite good at reading the AST, at least from Clang. By the way, if you dump the entire program here, it's not just a few lines. Okay, it's roughly about 200,000 lines of output here that just this thing gives you. This is one reason why I ask people if they submit issues to C++ Insights, get rid of the standard library headers if possible, because they simply let the AST explode. C++ Insights has different types of transformations. And this is good to know because it means you get different guarantees practically. So we have something that's more like pure AST-based transformations. That means I'm simply using what AST gives me and put it back out. So pure AST-based are making implicit conversions visible. Auto type deduction, so the resulting type from auto, the compiler directly knows that and then tells me that. Default parameters, const expr if, we directly can see which branch is active and which one not. So this is what the compiler in the front end already does. And a couple of other things like constant folding, so 7 plus 3 is 10. This is what the front end also does as well. And then we have a part that I call C++ standard-based AST transformations. That means the thing we saw initially with the range-based for loop, where the standard itself or a paper that contributed to the standard lays out how a certain feature translates to C++ code. So I'm using that then there. Range-based for loops, lambdas, no except, or what we saw but I didn't mention, that main, if you don't do anything, implicitly returns 0. Simple things like that. And then we have the difficult ones, the hand-rolled transformations. I was for a long time very reluctant to really release that because they can be buggy, incomplete, because it's such a complex language. So heavy hand-rolled transformations, one example for that we will slightly peek into are coroutines. So I can show you what's behind a coroutine. And that's 100% hand-rolled, because for coroutines, I think for all the major compilers, but at least for Clang, they do the heavy lifting in the back end. So the front end only has a tiny portion. You can't do anything real good in terms of transformation, because the hard things are done in the back end, the things that we really want to see. So I had to do a lot of digging and reading to get it as good as I think it can be. Yes?
That list, is it like always done automatically, or are these options I can turn on and off?
Sorry.
This list of transformations you're showing, are they all always done, or is there like options to turn them on and off?
So these here would be, sorry, I didn't mention that. C++ Insights basically is a command line tool, so you can run it from the command line. These are the command line options that it takes, And on the website, you have a drop-down menu where you can select them. So by default, it does the pure AST-based and a good portion of the C++ standard-based, but not the hand-rolled things.
Okay, because after the talk, then I'll ask you because I couldn't find that any configuration on the website.
It's where you select the standard. So there is one little down arrow thing.
Yeah.
And if you scroll down in that box, there it should be.
Okay, I see.
Maybe I can show it as well then when I move the next time. All right, perfect. So let's get to something real, because whenever I give a talk, I wanted to share something, give you something that you can learn and not just present the tool. I think it's nice, but let's see what's in the language that you might not have been aware of. Default parameters. So I guess everybody knows default parameters, right? I have this function fun here. It takes an integer x, which is defaulted to the value 23. And then I have this function use, where I call fun without passing any arguments. And of course, this code compiles, this code works, and we know fun is called with the number 23. How does it work? Any clues? Yes, please. Oh, wait, the microphone.
Just puts the function in, invocation with the default value?
Yes, perfect. So it works the way that we have the code here, and I transform that, then every call to fun essentially comes with my default value. So in all call sites, the omitted parameters, my default parameters, the compiler simply injects the value. That's great. I think it's simple. It was one of the transformations that simply plopped out of C++ inside. I wasn't aware, and it simply worked. Okay, and for earlier reference, if I hit the drop-down menu here, there I can scroll down to more transformations. So this is where you can enable all the extra stuff. Okay. So here we have the default parameter. Here we have another one. This time my function fun takes a std_string x, and that std_string x is defaulted to hello C++ community. I'm a default parameter. Shouldn't you be aware of? I'm also exceeding the small string optimization here, by the way, with that string. And then I'm using it 3 times in fun here, simply because I can. What do you think now? It's the same pattern, right? The compiler inserts it in all the places where I left it out. So that means my 3 calls to fun here create 3 std_string objects, and they allocate dynamic memory 3 times, and of course they destroy it 3 times, and of course they copy that silly string 3 times into the freshly allocated dynamic memory. So that means default parameters, I think, are a great thing as long as you have built-in types. But once you start using more complex types or types in general that are somewhat resource sensitive in your context, then maybe a default parameter can be something really costly. Okay, so this is the learning here from default parameters. Bless you. Here's another thing that I picked up in my very early days because I did a lot of networking and low-level implementations. And the major thing there is padding and alignment. Padding mainly, but alignment comes with that. So every data type in C++ is aligned at a certain address, and if necessary, it gets padded such that everything works out fine. So assume we have a 32-bit integer. Can anybody tell me what is the size of data here in bytes? Yes, please. 12. Everybody agrees with 12? The answer was faster than the microphone was running, so perfectly. All right, yeah, the right answer here is 12. And if you look at that with C++ insights, And this time I have the show padding information transformation enabled. Then we can see, and this comes directly from your compiler, it tells me that the size here is 12. And the alignment of the entire data structure here is 4. My integer starts at offset 0, has a size of 4. My character here starts at offset 4, has the size of 1. And then in here I have 3 padding bytes. Because my float needs to start at an align address, and it requires an address that's divisible by 4 because that's its size. So I have the padding in here. I can optimize that, at least slightly. One way to go here is to say we start with the largest type in a decreasing order. So I could put the jar at the last, as the last member in there, but I still get a padding bytes. Everybody knows why that's the case? Alignment. And the reason for that is arrays. If I would create an array out of data, the second member in the array needs to be aligned as well. And without the final padding, that wouldn't be the case. So padding, an interesting thing here. But why do I bother you, right? I mean, 3 bytes on these days machines, who cares? Let's consider a slightly different example. I have this struct apple, comes with 3 data members, a bool ready for write, an integer array data of size 15, and another bool have data. And then I have this update function here, takes an integer, returns void, does something, not our concern. Padding, right? So if you look at the padding here, and change the standard library first. Now here we go. Then we can see, oh yeah, here's a few padding bytes in between, right? 3 after the first bool, 3 after the last bool. So entire structure here sums up to 68 bytes. I mean, that's not terrible. Who cares about 6 wasted bytes? Most people don't. This here is the same code, this time in the other tool, right? In Compiler Explorer. Don't mind the update code. It does a few things down there to get the compiler to do something. And in the end, it simply tries to create around 2,000 of these, or 1,600 of these apple structs and accesses them in a random order. And the timing here is that it takes 1.81913 milliseconds to be executed. Just a number. What if I rearranged my data a little? Oh, look. I got faster. Because with the now structured data, a lot of my padding goes away, and the struct here fits nicely into 64 bytes. And that, by the way, is the cache line size on most architectures. In the way before, I had a lot of cache misses. And this is why it was slower before. So we might not care about the wasted bytes, because you have a lot of memory. But you might care about the speed and exhausting your cache. So this is why padding here might be something you want to consider. So here's one thing more, and I think this is one of the most difficult things in our language: lifetime, object lifetime. And the problematic part here is that a destructor, believe it or not, is not part of the AST. Destructors are handled in the backend. I can only speculate why, and I'm not sure whether other implementations do that differently, but at least Clang doesn't show the destructor in the AST, so no chance there. But they tell me when they're creating temporary objects, and I know the lifetime of temporary objects. They end at the full expression, or they also tell me when it's lifetime extended. So I can guess the destruction pretty good. What I have here is this struct apple. It contains a std vector of int v, and I have a free function fun here returning a apple object. And then I have this function use, where I use two range-based for loops. One loops over all the elements of fun.v, and the other one is only interested in the first element from v. Because I have a vector in a vector, I know I'm only interested in the element 0 from this vector. It's another vector, so loop over that one. What do you think? First one contains a temporary object.
They both do, but the second one is UB.
So the other answer is both contain a temporary object, but the second one is undefined behavior, UB. Okay? Let's see. So this here is the code, and this time I'm using the show object lifetime transformation here. And if I do that, then we can see first part is boring. We can see certain things here. So first of all, you can peek behind what a range-based for loop is, opening the scope and closing the scope. All in between is our range-based for loop. So we have two of them. And for the first, we can see here, I'm calling the function fun, and that one gets assigned to a temporary object. So this is what we said. We have a temporary object there. And I need a name for these temporary objects, so I let them start with the name temporary. And the rest of the name here is the line number and the column where that thing appeared. I initially started with thinking I'm smart and the column number is enough, but if I have multiple temporaries in one call, it's the same line number. So everything you see there, whether I have to create it by hand, it always is line number and column number. And we can see the object here then gets destroyed in line 33, so after the end of the range-based for loop. So what we established before, we have a temporary here, but that one is safe because the lifetime spans over the entire range-based for loop. It gets lifetime extended. For the second part here, for the second range-based for loop, we can see it starts the same. We have this call to fun, another temporary gets created, and then here I'm accessing the element 0 of my std vector v. But this time, my temporary object gets destroyed immediately after I assigned it. And since I'm assigning it to a reference, it's UB, as we said. Because once I enter the range-based for loop and try to work with the data is no longer mine. Maybe it's still there, and I get out happy because it feels like it's there, but technically it's always UB. Okay. So these are things that I now can visualize and show thanks to C++ and science. In C++ 23, I believe it is, this behavior is fixed. You get a lifetime extension for that piece as well. Nikolai Yusutis, you have to thank for. He fought hard to get that into the standard, but Clang at the moment doesn't implement that change, so I cannot show that to you. But in C++ 23, that should be safe.
So even if you change it up there, it still won't work?
What would you change? So the question is,
Standard level.
Yeah, so the question is, even if I change the standard level, it would not work. And yes, at the moment, it would not work. The standard has no impact because Clang itself doesn't implement it. So this is still open for implementation. So the standard level doesn't change anything. Yes?
Will CPP insights show the undefined behavior because, sorry, will CPP insights show the undefined behavior because the vector is empty and you're accessing the first element? Like, is there any indication that this is undefined behavior?
I'm not sure if I understand the question right. The vector is empty here, but I would rely on Clang, and Clang does not produce any kind of warning here. So Clang's output here is simply nothing. It's happy. So, and C++ Insights itself does not try to be a UB detector. So if the compiler shows it, I can show here what's going on, but I do not try to be a static analyzer here. So no, not more than that. You can explain it, but that's all. Let's stay with object lifetime. You all hopefully know the C++ standard. This is from the standard. I have this struct s here, and s contains an integer mi, as well as a stud pair of integers, which is a const reference mp. And now in use down there, I have an object a of type s, and I use uniform initialization, curly braces, to initialize the data here. I'm passing 1 to mi and 2 and 3 to my stud pair. And then I'm doing the same, but this time with a heap allocation. I'm using new. The interesting part is the uniform initialization remains. So question, is A valid? Is B valid? Please.
So I think A is valid because of lifetime extension and B is not.
Mm-hmm. Okay, we have one answer for A is valid, B isn't. We have another gentleman here saying B is also valid. Okay. Remember, all my code compiles, but some of the questions may be trick questions, right? So let's see. This here is the code from the slide, and this time I have show object lifetime visualization on. If I do that, we can see this time Clang itself starts complaining. So below here you have all the output the compiler prints to std error. So it tells me I have a temporary bound to a reference member of an allocated object that will be destroyed at the end of the scope. What's going on here? We can see I'm getting 2 temporary objects created. First here in line 16 and 17. And therefore my stud pair. My stud pair here takes the 2 temporary objects, and my stud pair itself is another temporary object, right? And I'm passing that one to the constructor of S for my object A. The nice thing is the 2 temporary objects for my integers, they go into my pair. My pair takes everything by copy, so they're fine. We can see their lifetime here ends directly after, we call that the full expression, so after the semicolon, while it's no longer needed. My stud pair, that would be this temporary 1116, we can see that one goes out of scope here at the end of the scope. Yes?
Excuse me, how do you know that it takes by copy? I mean, I see constructor call with 2 ints could be taken by const ref.
It internally stores it as a copy because I requested stud pair to contain 2 integers.
Oh, okay, so you mean that it internally it copies?
Internally. However, it takes it, in fact, you're right, I believe it takes it by const ref or even by r-value ref sometimes, but it stores it internally as copy.
Okay, that's what you meant. All right, thanks.
So now let's look at the second object, P. I once again get two temporary objects for my two integers here. I get another temporary object for my second stud pair, taking the two temporary objects for the int for construction. And then we can see my heap allocated as this time takes my temporary object of pair as a parameter. But now here, 1224 goes out of scope directly after the full expression. This is my stud pair. So immediately after I created this struct S, I have a dangling reference in there, which, by the way, is of course what the compiler told us already. And the reason for that is simply for A, we can, at least under some circumstances, make that thing work. Because A only lives on the stack, at least in my code. So placing the temporary object on the stack before and destroying everything at the end, you can lifetime extend that, you can make that work. For my heap allocated object, when do we use heap allocation? Usually if we want to have this object outlive our current function. But where would I place the temporary then? On the stack? That one goes away once I leave the function. So the only option would be allocating these temporary objects dynamically and destroying them, but that's a whole mess. A, by the way, also gives you undefined behavior if you return A, because the temporary objects live inside of main. Assume it's another function where they live. If you return A, the reference of the stud pair down is a dangling reference. So it's not 100% safe, but it's safer than the other option. Yes?
Sorry, the question about A. So you mean that lifetime of A basically ends after returning from the main function. What happens if instead of a pair, we have some object with a custom constructor and destructor? So you mean that the destructor won't get called after we construct A, after line 19, is that correct? So if we go back to the code.
On the left-hand side.
Yeah, right. So line number 11. So if instead of passing a pair, we have some object with a custom destructor, does it mean that destructor won't get called before line 12, basically? If we like
Around
print
line
statement
13, your destructor will be called.
there, at line, I mean,
You're talking about the destructor, right?
yes.
Yeah.
So if you mean that that pair object is still alive at line number 12, right?
So you're talking about
Line number 11. So we create a temporary pair at line number 11. So you mean that that object will still be alive at line number 12, right?
Yes.
So the destructor won't get called at line number 12. But doesn't that violate this standard because the object is clearly temporary?
The destructor will be called around line number 13. So this is the lifetime of your temporary to the end of your function. And if I would have an object with a destructor, we can do that later, but I don't have that much time. Then you will see that the destructor runs at the end of the scope. You can put printfs in between, and you will see the destructor will run later.
Okay.
This is lifetime extension.
Yeah,
So
thank you.
it's nothing special. It's just the the part when the destructor runs, and this is later. While you would see for line number 12 that it immediately runs after your new happened.
So the object P actually stays valid till exiting this function.
The object P itself you could return or use. The problem is that the reference.
Yeah, it will be broken after,
Yeah.
but lifetime ends actually happens after return 0, right?
Because this is main here. Yeah.
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 So it stays valid in this scope, in this small scope.
No. For P, if I would have something in between here, something like that, and we assume again that we are not passing a pair, but something with a destructor that prints out when it gets called, the destructor output will be here, before the next line. Because my stud pair gets destroyed, we say it's the end of the full expression. Once this expression is over, the semicolon usually is that point. So the destructors for any temporary object I created in here that does not lifetime extend gets called here between line number 12 and 13. So would you start using P inside main and access the reference here? It's always dangling. You might not experience that because your stack might not go away. And if your destructor doesn't do any freeing and zeroing, it's not easily observable maybe. But in terms of the standard of any analyzer, they will tell you it's UB because it is. We have another one, and this one is from C++ 23, or no, from C++ 20. It's P0960. We have a struct A here. It takes an integer A and an R value int R. And it has a function f that returns an integer. And I have in use then an int n with the value 10. And I have the 5 objects, A1, A2, 3, 4, and 5. And the paper here proposed that aside of uniform initialization, curly braces, we can also use parentheses to initialize an aggregate. And this is what I have here in line number 2 in form of A. It's just a struct, it's an aggregate. And before C++ 20, we always were required to use curly braces to initialize that. But since C++ 20, it came in mainly for generic code, we now can use parentheses as well. Now I have A1. A1 here initializes the first element with the number 1 and the second with the result of my function call f. And then I have A2 here that does the same thing but with parentheses. I have A3 that doesn't compile because it would narrow. That's not allowed in uniform initialization. And then I have A5 that uses parentheses, so it can narrow. It can pass a float here. And I have A5 that also puts a float in there and uses a student move. It's about lifetime again. So A1 to A5, do you think they are all valid? Any objects in where you say they dangle? They bind to a temporary and that doesn't outlive them.
Something broken is A2.
A2 is broken?
Will be broken, I suppose.
Okay, we have 1 vote for A2 being broken. So let's see. If you look at this, then we can see for A1, I get a temporary. That's the result of my function call. That one gets passed here, and the lifetime of that ends after my scope ends. So A1 is perfectly fine. A2 here also gets a temporary. That one gets passed to the constructor of A2, but it gets destroyed immediately after the end of the full expression. So the difference is for uniform initialization, you get lifetime extension. For parentheses, you don't. So you can see this pattern for the rest of the elements as well. They all get destroyed if you pass a temporary to them. So this is the difference between uniform initialization and parentheses here. So if you're a fan of parentheses, please be aware of that. And maybe we need a microphone in the back here. Thanks.
Could the comma operator be used after, say, A2 was declared, to do something with it before the semicolon?
After A2 was declared.
So on line 21, after the last parenthesis is closed, could a comma operator be used to do something with A2 before you get to the semicolon?
I cannot answer that. Because in this context, I'm not sure whether you could access A2 or whether you can only declare a new variable of type A. Okay, if the first part
Okay,
is
thank
is possible, then yes, you could do something, and you would get a lifetime extension. Yeah, until the semicolon. All right, reference parameters. I have a printInt here function, takes a const int by reference, uses C++23 to print out the magic number is with a std print ln. It's perfect. And I use that one with the number 43, which incidentally is the floor number we have here. Is that code fine? See a few nods? No problem? All right. I can turn that around and can say, okay, I have this lifeguard object here. And the purpose of lifeguard here is that it has a puts in the destructor and in the constructor. So I can visualize that the constructor runs, then my output comes, and then the destructor comes before I leave the scope. So everything fine as expected. What if I do a small change? Have you seen it? I'm changing the return type from void to task because I'm no longer returning, I'm co-returning. So the beast now is a coroutine. And the coroutine has the ability to sleep at certain points and become resumed later. So the question is that safe? And this is where C++ Insights comes in. This is actually why I started doing the coroutine transformation. So the first part here is not interesting, it's the code I wrote to make this thing work. So here we have it. The first thing that the compiler creates is the coroutine frame. All the data we have in a coroutine, may be local variables or parameters, end up at the coroutine frame. Coroutine frame also contains a resume and a destroy function, the promise type, and a lot of other things. Among the thing I'm interested in here, my const lifeguard reference num, my parameter. And then the next thing the compiler does is it splits up the function, the coroutine function rewrite, into two functions. One you can see as a setup function, and the other one is the actual function doing the work you want. In the setup function, this is what we're seeing here. The compiler allocates the coroutine frame, sets it up, creates the promise type, and this here is not technically 100% valid because we have a const reference, but this should visualize the assignment of my parameter to the coroutine frame. The problem now is, since my parameter was a reference, and this same type as a reference is echoed in the coroutine frame, once the coroutine gets paused for the first time, my temporary object gets destroyed. So whenever you pair something by reference to coroutine, be aware that if it ends in the coroutine frame, it might go out of scope way too early for the coroutine. And this is what C++ Insights here can visualize you. We have not enough time to talk about coroutines here and the rest of that, but this is the main part. Be cautious parsing references to coroutines. Let's talk a little bit more about C++23, the deducing this feature, right? We can have an explicit object parameter to reduce our code. What I have here is a basic implementation of a std array, and we can see I have the function data, begin, and the array index operator and size. Yet, for the first four functions, I have two versions of them, the const and the non-const overloads. So this adds a lot. And in C++23, thanks to deducing this, I can reduce that to really only the 5 functions that I need and not the 9 that I had to write before, because deducing this here adjusts to the const and non-const version my object gets called with. And this is a feature I really like, not just for me being able to use it later, but also because it simply worked in C++ Insights. I didn't have to do a single thing for that, because if I transform that, we can see what compiler did is all my functions that use the implicit object parameter are templates. So it's just a function template, it fallout, and here we can see I have one instantiation for a const array of type int of size 2, and below here I have the same one just for the non-const version. And this is how it gets adjusted very easily. So that using this for C++ 23.
Can I ask a question about the previous slide? Or the compiler insights window you
Sure.
showed? So that's
Oh,
not
should I
the
do?
actual window.
Oh, sorry. Was too quick closing that one. So here we go.
So I'm wondering why it still shows auto on the right side for the
Line
templates.
44, for example.
For example.
There is one big secret I usually don't tell people outside my training classes, but one very easy rule in C++ in C++ is compiler is lazy. Deducing the type of auto here is impossible at this point because we are never using this function. So the compiler doesn't know it under all circumstances, and the other thing is even if it knows it for methods inside class templates, it doesn't bother creating them. If you don't use it, it simply costs you compile time. And if it can prove that you will not use it because you have no call to it, why bother wasting that time? So this is why, that's a good observation, in a few cases you still see auto. Or here as well, no implementation. Because it's not called, it's not used. You're welcome. All right, how about going a little bit back to the basics? It's not CppNorth here, but we can go back to the basics. Let's say 1986. The recent thing I built, and this is why we have the lifetime visualization in C++ Insights, is a CFront mode. Because this helps a lot explaining things under the hood. So what I have here is a very simple piece of code here, right? And if I now enable the show C++ to C transformation, I know it's a C++ conference, it might be a little hard to show you C code, right? But it helps explaining the constructs. Then we can see things like, oh, yeah, a constructor is nothing than a function with a special name. Technically, you're not allowed to take an address of that function, so it's a little bit more special. And we can see things like, oh, the first parameter to each member function carries the implicit this. So I can show things like that. And I can show things like for my member function set, which is not const on the left-hand side, my this pointer is not const. But for my member function get here, my this pointer is const because my member function is const. And this is how it translates. And yeah, this helps explaining things sometimes if you want to go deeper. And it helps answering a question that I get a lot. How do virtual member functions work? Or vtables? And this is something your compiler can visualize you. They can dump the vtable layout, but I never found that quite pleasing. So here we can see, and this is more or less what CFront really did. I have a working CFront version. So we can see here for my fruit class, I have a virtual destructor, I have a member function fun, and then have a class apple that derives from fruit. It adds some member that we see a data member, it overrides fun, and then I have a special sort of apple, pink lady, they're delicious. So that one overrides fun once again. And in main here, I create a pink lady, call that object delicious, and I call fun of that, and I downcast or upcast it to fruit. And the ugly version you see on the right, this is what a compiler has to do to adjust the disk pointer and to find the correct entry in the vtable. So I'm still not sure whether it's the better version than Clang dumps if you request a vtable layout, but this is C++ code, and I think you can work better with that one. And this is also the first and so far only fix I did in an airplane, because it didn't work entirely before I gave the talk. The constructor here for Pink Lady didn't set the vtable pointer. Okay, so feel free to play around with that. Yeah, do we need a microphone over here maybe?
On line 144, there's something happening after the return. What's going on there?
Yeah, my apologies for that. That's a good question. So in line 44, I think it's very obvious what's happening here. This is the call to the destructor. It's easy to decipher, right? Because it's a virtual destructor, we have a fetch of the vtable, and I didn't know where to place it. So before the return is wrong if you have an object where you call get and return a result of that, but doing it after return is obviously wrong as well. So yeah. Comma operator return, something like that. Yeah, maybe. I have to come up with a more clever solution here. So I think we are exceeding our time a little today. Sorry about that. So you can support a project if you want with patches. Of course, they are welcome, but issues are fine as well. If you help me figuring out what's wrong and I fix it, it's perfect. You can become a GitHub sponsor. That's the latest edition, or you can buy yourself a nice T-shirt with the C++ Insights logo and support the project with that. This is a question I got 2018 and tells me how quick time passes by, right? And the person here obviously knew a little bit about German, or maybe did speak German. The question is it completely fertig? And the answer is it's not. We are developing new C++ standards. There are a lot of things I think I could do better or missing. So it's not complete yet. And I hope we have a brief time for questions, but before we go over to questions, I'm Fertig. Thank you. Thank you. Thank you very much. Do we have time for questions? Maybe like 3 minutes. 3 minutes? All right. 2 to 3 questions. Anybody?
So first of all, a microphone is not an ice cream cone. Don't treat it like an ice cream cone. Point it at your face, okay? One of the things that I want to pay very close attention to is a lambda with the value being passed into it, and the function is asynchronous, so I want to know that its lifetime is actually going to survive. Will this show me?
The asynchronous part could be hard because you have to think about that in your head, but lambdas where you pass parameters into, this will be something that C++ Insights can show. Yes. If you want, we can, after the presentation, code something. Other questions? It's right before lunch, so everybody is thinking about lunch. All right, then I will not stall you any longer. Thank you very much, and see you.